in this lecture we are going to talk about digital PID control implementation using Verilog HDL programming. In fact, this is a continuation of the previous lecture, where here we are want to emphasize especially on the PID controller part. So, we will take PID control implementation and Verilog coding. First, again we recall that our digital voltage mode control, where we are concentrating only this particular part. That means, if we take the overall block that we want to design for this digital controller, we know there are sub module and we are only emphasizing the digital PID controller. So, this part we are going to highlight. So, in this part, the main module, again this is a main module, digital main module, and we just want to highlight our I would say the voltage PID controller part. So, main module, again it is calling TPWM, DAC clock, all these interface we have discussed in the previous lecture. Now, we want to emphasize this particular block. What is the input to this block? So, if we consider this digital PID controller, I am talking about, that means a PID, okay. So, it is a digital PID controller, digital PID controller. What is the input? So, one input is your error voltage, which is NE, and it is in the format of Q1.9. What is the output of this controller? It is the N-con, that is the controller out, and we will decide what is the size of this controller output. But what else we need? So, we need all the parameters, Kp, we need Ki, we need Kd. What else we need? We also need FSW for this block, because when you calculate, if you remember that derivative control, for example, Qd, we know that Ne minus. So, if you take nth cycle minus Ne n minus 1, that means there has to be a delay. So, that means this delay has to be generated with respect to the switching frequency clock. That is why we need a switching frequency clock for the synchronization. Also, for the integral control, we need the additional block, like a previous value we have to add. It is an incremental integral control implementation. So, for that kind of summation, we need to synchronize with the switching frequency clock. So, that is one of the input. We can provide other input like a flag, that means if there is a saturation in the PID controller, then the flag can be high. So, you can always add additional thing, but these are the mandatory requirement. This is the overall PID controller simple implementation, we did it in MATLAB. When you say this block, the delay, right. So, this delay, again this delay should be with respect to clock, and this we have discussed. This delay is basically a register, and this register will be synchronized with the switching frequency clock, and this register will have a data in. Again, this is a vector data, and you will have data out, and the size of the input and output vector data same, and the data size will define the size of the register, whether it is 8-bit register, 6-bit register, 10-bit register, whatever. So, same thing we require for this register, and we have discussed that in MATLAB how to build the custom model using difference equation rather than using plug in any Z transform or any transfer function. That also we have discussed customize. And in the subsequent, maybe at the towards the end, we want to see if we have a realistic MATLAB model and then an actual experiment, then how close they are there. They may not be close, but how far, I mean what is the deviation, how much they can capture the transient behavior. So, we want to discuss this aspect as well. So, here the main module, again it is calling, that we have discussed, but now where sign parameters we have defined. So, this up to this point is a main module declaration we require, because we need to see the values of the parameter, that is a part of the main module, the N out and Kp, Ki, Kd. Okay. Now, this module was called, if you recall in the previous lecture, we have instantiated the module named digital PID controller. Now, we are talking about that particular module. What is the input to the module? We have discussed that input to the module is a switching frequency clock. This is the error signal, the locally error signal we have discussed. This is the controller output and these are the parameter Kp, Ki, Kd, and we discussed that these are the bare minimum requirement. That means, we need the error input. In this case, this is the digital representation of this. We need this parameter which is this parameter which is this, and this parameter which is this, right, and we need this output which is this, right, and we need all this register to be synchronized with respect to this clock. So, these clocks will be used to generate this delay, it has to be synchronized. Next, we have to define what is input, what is output. We know that input is PWM switching clock and there is a scalar, but there are vector input like error voltage, Kp, Ki, Kd, and all we are writing in 10 digit number, but their Q format are different. So, for error voltage, the Q format is Q1.9. For proportional gain, we took Q4.6. For integral gain, we took Q1.9, and for the derivative gain, we are taking 4.6, which means all numbers are 10 bit number, 10 bit sine numbers. They are represented by the same vector size, but their Q formats are different, and we have discussed that if you multiply, add some different format of number, we need to synchronize, we need to scale, normalize them, otherwise you cannot add. So, their Q format must match. Now, the output signal is the controller output, and you can see clearly it is a 19 bit number. So, it is a 19 bit sine number, but we are yet to define that what is the size, is a sine number. So, we are internally variable some temporary value. Okay. So, we can check and see whenever we multiply, let us say we multiply Kp into Ne, Kp is Q4.6, then this is Q1.9, and we call this to be N proportional temporary, and that is why you can see their bit size is 19, because their size will be Q 5.15. But what is the problem? Each of these are sine bit, and if you multiply to sine bit number, then resultant there will be 2 sine bit, that means 1 you can discard. So, this will be normalized to N proportional, which will be in the Q 4.15 format. So, it is a 19 bit number, and that is defined here, all these 19 bit. That means, this is the resize data of the proportional term, and we will talk about resize data of the integral and the resize data of the derivative. We will come to that point. So, then these are all internal declaration. We also need a previous value of error voltage, because error voltage we know NER. So, this is the error, that means, we have NER which is the error, which is Q1.9, and we also need KNER previous, which is also Q1.9, because for derivative control we know that. So, derivative will be Kd into NER minus NER previous. So, we need this previous, and that is why we have declared where, sorry, register, because we will make just a shift operation, and that we will discuss. Next, we are computing the derivative action, because we have to create a previous value. and that is happening with respect to the switching frequency clock. All this previous update will happen with respect to the switching frequency clock, because the data are captured, output data are captured with respect to switching frequency clock. So, with that clock we have, and we are calculating error at that clock only, and we are calculating the previous error with that clock only. So, that is why the always block is there. So, always derivative temp, which is k d into NER minus n previous. What is n previous? After. So, here we are using blocking statement. You can use non-blocking statement, there is no issue, but I just want to avoid. So, that means this line will be executed first and then this line. So, that means in the first line it will take the previous value which was stored in the previous cycle. Once this computation is over, then the instruction will come to this, and then it will take the previous will be storing the present value at this point of time. Then this process continue. When next cycle it will come, NER will be updated with the new value, previous will be storing the previous NER value, and the action continue, and these things we know. So, this is clear, but now this one, since we are multiplying k d to be q 4.6 and this whole operation is q 1.9. So, then the resultant here it will be q 5.15, and we are resizing the proportional control. What are resizing? We are simply discarding the 19th bit. That means, this is another MSB we are discarding, because there are 2 sign bit, 2 MSBs which are sign bit. So, we are discarding the MSB. Similarly, we are resizing this bit also, and we are also resizing the derivative by discarding the MSB. So, these are all things are resizing, I will say resizing by discarding the redundant sign MSB bit. Okay. Then here we are doing integral control. So, if we go back the integral control, you will see so this proportional we have discussed, this will be q 5.15, because this guy is what q 4.6 and this guy is q 1.9. What about this q 1.9? So, what will be this? It will be q 2.18. So, we need to resize. That means, we need to resize, because we know that u I of n will be u I of n minus 1 plus k I into V error. So, this we are writing in any, because here it is any, and that we did in the previous. So, this is the operation k I into any, which NER is the error voltage, and we are resizing this because we need to resize. Then now again integral has to be computed, because you need a previous value. So, first a temporary variable, and this one is already there, and this is some another temporary variable. So, you can think of a previous value. So, this will be n integral previous, that means, this you can think of this is like n integral previous. So, this is loaded with the current value. That means, whatever we will do calculate in the same cycle after this line is executed, we will take u n minus 1 is equal to u I n, and then cycle continue. So, these values will be now stored as a previous, it will be used in the next cycle operation, and this is exactly happening inside this block. Then once you have done, then the actual instantaneous integral value, we are, you can see what is the size of this data. This data we have made q 1 dot, because if we remember that this is 2.18, we have resized to q 1.18, it is a too large data. So, we have integral instantaneous, I would say instantaneous value, or this temp, okay, maybe. So, here these are all internal variable name 4. This is in the format of Q1.18 and we have n proportional in the format of Q4 dot, because after resizing 15 we have n derivative, it is in the form of Q1.15. So, we cannot add them. What we have to do? First, this data we have to pad with, like we can make sign bit extension. That means, we have to extend this sign bit 3 times, because we need to make it 4. We need to convert this into 4.15. Okay? And then we can discard 3 LSB, because it is up to 18. So, we can discard, because otherwise we cannot resize, or we can pad with 0. So, there is no point, we can discard it. So, either you can discard this or you can resize. If you resize, adding with another 3 zeros, actually size will go up. So, it is a designer choice. So, you are padding with 3 sign bit. In fact, it could have been 3 in this sign bit, but for some reason actually the Verilog was giving error. So, I have manually made 3 sign bit, is a concatenation operation, and here I have discarded 3 LSB. So, that this number now become Q4.15. Now, we are making it is a saturation limit, because there is a high chance the integral gain will saturate, and because it is sign number. So, if this number exceeds some upper limit, which again is defined, the upper limit is defined some number. So, I can set some number, it is your choice. I am not going totally full upper limit of the dynamic range, leaving one space down, that is the upper limit. If the integral gain reaches that, then we will simply set the maximum value, otherwise it will take the current value. You can also set the lower limit as well, no problem. Once this is the actual integral gain, which coming from the saturation block, that means we are putting a upper saturation limit. Lower as if we are not putting, but we can put it, and this is my n integral. Before that it was n integral instantiation block. Once it is generated, now we are adding. So, this is this particular value n proportional, we are adding n derivative, and this is my n con. Since this number is 4.15, this number all are 4.15, 4.15. I am also taking 4.15, but there is a possibility that there can be overflow. So, that can be taken care, but otherwise it is a 4.15, it is a 19-bit number. That is why what is going out is 4.15. So, here again you can take another. So, it makes a little bit complex, but it is unlikely that all will add up and exceed, but there may be possible if your gain is high, otherwise they will actually come under this 4.15. So, in summary, we have discussed digital PID control implementation, and we have also discussed Verilog HDL coding for digital PID control implementation, and we will discuss about the live demonstration this PID controller, the transient response in the subsequent lecture, and that is it for today. Thank you very much.